Hello and welcome to YourPedia. My name is Aman Sharma and I am your mentor for CSC at YourPedia. So today we will be solving some past year NIC questions and that were asked in the NIC exam. The topic that we have selected is data structures and algorithm. So first question is, what is the time complexity of the following function? Now, first of all, there is a loop for a is equal to 1, a less than equal to n, a plus plus. Then there is another loop, nested loop for b equal to 1, b less than equal to log a, b plus plus, and then the function will be printed. So if we want to find the time complexity of this function, first of all, for initially a is equal to 1, now it will run for, start from b equal to 1 and run till log, when b is less than equal to log a. Now value of a is 1, so it will run till log 1. Now log 1 is nothing but 0. So it will run till b, when b is less than equal to 0, but b starts from 1. So it will not run for the first pass. So it will not go inside the loop because this statement will fail and will come out of the loop and a will be incremented. Now after a is incremented, it will again start the loop for b. So b is equal to 1 and it will run till b is less than equal to log a. Now log a is nothing but when a value is equal to 2, it will run till log 2. Now log 2 is less than 2, so it will not run for b is equal to 2 because b is equal to 2 is not less than log 2. So it will again run, it will run only one time. After that, for a is equal to 3, it will run for 1. For b is equal to 2, again it will not run for b equal to 2. So similarly, it will keep on running like this and a will be incremented and b loop will run till it reaches log a. So let's say that a value is equal to k. So it will run, first of all it will run for b is equal to 1, b is equal to 2, b is equal to 3, and it will run till b is equal to log k. So this will be printed this much time. Let's say that we reach another value, a is equal to m. So it will run for first b is equal to 1, b is equal to 2 till b reaches value of log m. So this will run p times, p times, p times and p times. So as a whole, this ran for log k times because 1, 2, 3, 4 up to log k. This ran for 1, 2, 3, 4, 5 up to log m. So this ran for log m times. So when we reach the value of a is equal to n, this b will run till how much? 1, 2, 3 up to log n. So this will run for log n times. So if you want to calculate the time complexity, the time complexity can be the total number of times this loop ran. So for a is equal to 1, this must have ran for log 1. Second time it ran for log 2. Third time it ran for log 3 and till the end it ran for log n. Now these are approximate values because we are finding the complexity in asymptotic terms. So you can round off these. You don't need to write this as 1 because it ran only for one time. We will be taking the approximate value. So log 1 plus log 2 plus log 3 up to log n, this will be the value, the times, how much times the may function will be printed. Now if you use the property of log, if all the logs are in addition, you can convert it to one single log and all the items inside will be multiplied up to n. Now this is nothing but n factorial. Now we calculate the time complexity in asymptotic terms and we use big O notations to calculate them. Now big O is nothing but upper bounds. Upper bound. So if we take the upper bound of these elements, so n will always be greater than this one, n will be greater than 2, n will be greater than 3, n will be greater than equal to n. So if I round this off to bigger terms, or you can say upper bound of the system, this n factorial can be written as n raised to power n. This is how big O behaves. So this will be n raised to power n, and if you solve this further, it will go to, you can take this power of n to the front in the multiple of log, and it will be n log n. So the time complexity will be order of n log n. So the correct option will be option C. So this is how you solve the time complexity problems in the algorithm subject. Now the next is, let T be a binary search tree with 15 nodes. So T is a binary search tree with 50 nodes. What is the minimum and maximum possible heights of the tree are? Now, binary search tree, how binary search tree behaves is, if you put a value which is less than the root node, it will go to the left, and the bigger value will go to the right. Let's say if 20 comes, 20 is greater than 10. Here it will come, 20 will be greater than 15. So it will come here, and if you take a value as 17 or say 14, so it is greater than 10, it will go to the right, it is less than 15, so it will go to the left. So 14 will go here. Now what is the maximum and minimum possible height? Now let's say that the numbers are in the array that you give to the binary search tree is in ascending order. So the array is 1, 2, 3, 4, 5, 6 up to 15. So when the first node comes, 1 will be put here, 2 is bigger than 1, 2 will come here, then 3 will come here, then 4 will come here up to so on, and 15 will come here. Now for 2 nodes, if you take 2 nodes here, the height is 1. For 3 nodes, the height is 2. For 4 nodes, the height is 3. For 15 nodes, the height will be 14. So maximum height that a tree can have is 14. Now for the minimum height, now minimum height will be calculated by the fact that minimum height will come when you distribute these nodes in a very even and very efficient way. How you can do that? Let's say that this is the 10, 7, 16, 4, 9, 12, 20. Now these are evenly balanced. This is a full binary tree which is evenly balanced. Every node is having two child. Now if you give it further nodes 5 and 8 will come here. So let's take this as 11. So 10 will come here. So okay, let's take this as 13. So 12 will come here, 14 will come here, 19 will come here, and 21 will come here. Now you can see there are 15 elements in this, and this is the minimum height that is possible when you divide the numbers or nodes in even terms in a perfectly balanced tree. So this is how you get the minimum number of height. So if you want to get the maximum height, you need to divide it unevenly, or you can say you go to the one side only. If you want to get the minimum height, or you can say the height will be minimum when tree will be all the nodes will be used efficiently, then the height will be minimum, and the height is nothing but 1, 2, 3. So this is the first level, this is the first level, second level, third level, and fourth level, and the height for these levels is, for this one, 1, 2 and 3. So the minimum height is 3 and the maximum height is 15. Now there is one more thing. If you take height as h, there is a straight formula. If you take height as h, then if you divide all the elements in a perfect order, then 2 raised to power h plus 1 minus 1 will be equal to the number of nodes. And if you put this in this formula, 15, so 2 raised to power h plus 1 will be equal to 16, which is equal to 2 raised to power 4. So this implies h plus 1 is nothing but 4, so h is equal to 3. So this is also, you can calculate the height, but you can also see how the system works. Now the next question is the number of distinct spanning trees, minimum spanning trees for a weighted graph below is. Now minimum spanning tree is nothing but the graph will be we will select the edges and nodes in such a way that it behaves like a tree. Now tree will not have any cycles. So tree will not have any cycle. So it will not have this kind of node here which will make a cycle. So you have to take the minimum spanning tree. Now in minimum spanning tree, the weights should be minimum. So you have to select the edges and nodes in such a way it behaves as a tree. It covers all the nodes of the graph, and third thing is the weight should be minimum. So how we can do this here is, first of all, let's first you can see it properly. So first of all what we can do is we will mark the nodes, and then we will select the so these are the nodes. Now first of all just take all the minimum nodes or all the minimum vertices, all the minimum edges which are having minimum weight. So first of all we can take this one which is 1, 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 and we can take this one which is 1. Now we have covered almost all the edges, but the tree is not connected. Now one more thing, let's say if this was, let's assume if this was also 1, now you could not have taken this, because if you take this it would have made a cycle in the graph. So you have to take the minimum edge weights, and you have to take care that while taking these minimum edge weights it should not make any circle or cycle in the graph. Now when 2 is concerned, now first of all in order to join the first of all let's take this one. Now there are, for this element, in order to join this part of the tree, these two parts of the tree, this edge is necessary. You have to take it. There is no other option other than taking it. You have to take it. So first we will take this 2. Now after that, next is you have to join this part of the graph with this part of the graph, and this part of the graph with this part of the graph. No need to take this 2. We don't need to take this 2 because then it will make a cycle here. No need to take this 2 because it will make the cycle here. Now after that you can take you have 3 options here. First option is taking this 2, second option is taking this 2, third option is taking this 2. All these will connect the graph. So you have 3 options. You can take this one, or you can take this one, or you can take this one. And as far as this is concerned, you have 2 options here. Now let's say I choose this one. Now when I choose this one, this is a graph right now. Now I have to choose from these 3 also. Now if I choose this one, it will be a spanning tree. Instead of this, if I choose this one, it will be a spanning tree, and if I choose this one, again this will be a spanning tree. So by fixing this one, I have 3 different spanning trees, and there are 3 different spanning trees which we have selected. After that, instead of this one, if I choose this one, again I will have 3 different options. So I will have 3 different spanning trees here. So total number of different spanning trees that are possible for this are, minimum spanning trees possible for this are 6. One more thing that you can do here is you can use permutation and combination. Now you have to select one node out of these 2 nodes. So there are how many options for this? 2C1 into. After that you have to select one node from these 3 nodes. Again you have to choose one from 3. So it is nothing but 2 into 3, which is also equal to 6. So the different type of minimum spanning trees required are 6. So the next question is, what is the time complexity of following recursive function? Int do something, if n is less than equal to 2 you will return 1, else you will call again the function do something, and in between you have square root of n plus n. Now you have to calculate the time complexity here. Now there are two ways to do this. First we will do the normal way, which is recursive function way. Now if the time complexity of this one, let's say, is t of n, and you have to find t of n, so in how it breaks is, it breaks into other do something function, which is t of function, and in t of function you have square root of n plus some extra time for plus n. Now this is a mistake that some people do, because when you do something, you will find the square root of n, but there is plus n. This plus n does not mean that it will take plus n time. It is a value function that whenever you find the square root of n, you will add the plus n into it. So you are not finding the value function, you are finding the time complexity of the function. And if you see here is, what I am trying to say here is, you will need some time to calculate this by using do something, but in order to do plus n, if you are a processor or you are a computer, in order to do n plus n, you will require order of 1 time, because it is just a single line. So plus n will not take plus n time, it will not take n time, it will take how much time? It will take just order of 1 time. So now you can solve this. Now in order to solve this, we will do simply what we will do. We will apply the master theorem, but we cannot directly apply the master theorem, so we will do some substitutions here. So first of all, put n is equal to 2 raised to power k. So t of 2 raised to power k equal to t of 2 raised to power k by 2, plus there is no k here, so order of 1. Now second substitution we will do is, put t of 2 raised to power k is equal to s of k. Now if you put this, s of k will be equal to s of k by 2 plus order of 1. Now you can apply the master theorem. When you apply the master theorem, k raised to power log 2 base 1 is nothing but k raised to power 0, which is equal to 1, and the function here is also equal to 1, so these are equal. So the time complexity will be nothing but k log 2 base 1 into log k raised to power, there was no log k here, so you can write log k raised to power 0. So log k 0 plus 1, which is nothing but log of k. So the time complexity is s of k equal to log k. Now the substitutions were s of k is equal to log of k. So first substitution we will change is the second one, because we will go in reverse order now. So put s of k is equal to t of 2 raised to power k. Now we are substituting s of k. We will not be touching this one, because we are only substituting s of k instead of t2 of k. So it will be equal to log k. Now in the first substitution, we did what? We substituted n with 2 raised to power k. So wherever is 2 raised to power k, we will put n there. So t of n, and if n is equal to 2k, this implies that k is equal to nothing but log n. So if k is equal to log n, we will put log into k. So k is log n. So time complexity of t of n is log n. So the correct option will be option D. Now there is another method to solve this. What is the another method to solve this is, we will be solving for n here. When it will call this function, we will be solving for n by root n, or you can say n1 by 2. After that, again for the third time, we will be solving for n by 4, or you can write this as 2 raised to power k, 2 raised to power 2, and you can write this as 2 raised to power 1. For the fourth time, we will be solving this for 1 by 2 raised to power 3, and let's say after k substitutions, after doing it for k times, it will behave like n by 2 raised to power k. Now our function will stop where? Our function will stop when the value of n reaches equal to 2. So when n of 1 by 2 raised to power k reaches 2, we will stop. So if we can find the value of k where it stops, we can find out how much iterations we did. So we can easily find it. How we can find it? Take log to both sides. So it will give you log 2n 1 by 2 raised to power k equal to log 2 base 2. If you solve this, log 2 base n is log 2 base n, and this will come into the multiplication 2 raised to power k, and log 2 base 2 is nothing but 1. So 2 raised to power k will go that side, n is equal to 2 raised to power k. And if again you take log here, take log to both sides, this will be log 2 base n is equal to log 2 base 2 raised to power k, which is equal to k will come in the multiplication. Log 2 base 2 is nothing but 1, so equal to k. So you have found that k is equal to log 2 base log 2n. So you have find out the number of iterations, which is the time complexity, how many times the our system will run. So this is nothing but time complexity. In that method the answer was also log 2 base log 2n. In this also it is log 2 base 2n. So I hope you understood the concept, and if you have any doubt you can comment down below, and I will try to solve your doubt. So I hope you like the video. Keep preparing and keep sharing. Thank you.